Hello everyone, welcome to lecture 6 on the topic of transformers. And in the previous lecture, we had seen modeling of resistance and inductance of the both primary and secondary of the transformer, how to transfer the inductance and resistance from one side to the other side, how to make the equivalent resistance refer to the primary or refer to the secondary and so on. So we had seen that. So based on that, let's solve some example problems so that we get better understanding of the things. We begin by this question that is on the screen. So you can go through the question. It is not any complicated or twisted question. It's a straightforward question. So you can try to answer this, and then you can compare your answers with my answer. So let's look at this question. So when you see this question, we have a 32 kVA 2200 by 120 volts 50 hertz transformer has high voltage winding resistance. So let's just write V1 is 2200 and V2 is 120 volts 50 hertz transformer. So from this I can get the ratio, that is K. K is actually V2 by V1. So that is 120 by 2200. So let's calculate 120 divided by 2200. I think we'd better keep it like a fraction. So I'll just put it 12 by 220. Resistance of 0.1 ohm and leakage reactance. So R1 is given as 0.1. X1 is, so this is in ohms, X1 is J 0.22 ohms. The low voltage winding side, so R2 is given as 0.03 ohms and X2 is given as 0.015 ohms. So this data is given. Find equivalent impedance referred to high voltage side, and so basically we have to find Z01 and Z02. So let's begin by finding out R01. So that is nothing but R1 plus R2 dash, which is nothing but R1 plus R2 by K square. So this formula we had derived in the earlier lecture. So such that the core losses are matching and all these things. So here we have R02 is R1 dash plus R2, whereas yeah, here it is. R01 is R1 plus R2 by K square, where K is I1 by I2 or V1 V2 by V1. So that is how we are getting this. So so let's define this. So I instead of working on the command window, I'll just write a small code here. So this is I'm defining the variables R1 0.1, X1 is 0.22i. So this is a complex number, so I'm defining like this. R2 is 0.03 and X2 is 0.015. So I have defined these parameters. Now K is V2 by V1. So where V2 was 120 and V1 was 2200. Let me just check it. Yes. So K is also defined. So now R01. So let me use capital R, is nothing but R1 plus R2 by K square. Similarly, X01 will be X1 plus X2 divided by K square. So it is just straightforward. then Z01 will be R01 plus X01. So let's run this code. So I have all the answers here. So R01 is 10.813. I think here I forgot to define I here. So let's run it again. Clear screen, clear all variables. So now I have the correct answer. So X01 is purely inductive and R01 is purely resistive, and then total is this. So I think I can just copy this. And finally I got this answer. So this is everything referred to the primary side. Now how that is the high voltage side. So how to find the impedance referred to the low voltage side. So let's do that. So I can right away do this. That is Z naught 2 equal to Z naught 1 into K square. So this is a direct step. So that will give me the value of Z naught 2. So I'm getting 0.030298 and so on, something like this. Now the alternate way of doing this is individually you find R naught 2, which is nothing but R1 dash, that is K square into R1 into K square plus R2. This is 1. And next I'll write X naught 2 will be X1 into K square into X2. And then I'll find Z naught 2 is nothing but R naught 2 plus X naught 2. This is another way of solving it, slightly longer way. So let's check whether we get the same answer. So again, you see this answer and this answer is exactly matching. So with this, I'll write Z naught 2. So these are two different ways of calculating Z naught 2. And this is my solution. So I think with this we have come to the end of this particular problem. So let's take up the next problem and then try to see. I hope your answers are matching with my answers. So let's continue. All right. So this is the example 20. The full load copper loss on HV side of a 90 kVA 11 kV by 440 volt one phase transformer is 600 watts, and on the LV side is 500 watts. So what is given? So again, goes without saying, you can try yourself to answer this question and you can compare your answer with my answer. But then let's do it here. So 600 watts is the full load copper loss on the HV side. So I1 square R1 is 600, where I1 is the or I1 FL. Similarly, I2 full load square R2 is 500 watts. So this is given. But then I can find out the full load currents right away. So how I can find the full load current? The rating is given. So I1 full load is the kVA rating 90 kVA divided by 11,000 volts. So this will give me the full load rated current. So you should be careful with the units. So 90,000 divided by 90 kVA divided by 11,000. So 8.1818. So I'll write 8.182 as a rounded figure. 8.182 182 amperes is the full load current in the primary. So from this I can find R1. So R1 will be 600 by 8.182 square. So that is 600 divided by 8.1818 square. I'll get 8.963 ohms. Similarly, from this I can find R2. So how do I find R2? First I'll find I2 full load, which is 90 kVA divided by 440 volts. That is 90,000 divided by 440. 204.55 amperes. Huge current. This is the secondary full load current, and the loss is 500. So therefore R2 I can find out, that is 500 divided by 204.55 square. 500 divided by 204.55 square. So I'm getting 0.0112. I'll write it 0.0112 ohms. So I have both the resistances. This is the primary resistance, this is the secondary resistance. Calculate R1, R2. Exactly, we have done that. Now let's calculate R01. So what is R01? That is nothing but R1 plus R2 dash, which is nothing but R1 plus R2 by K square. So which is nothing but, so R1 is 8.963 plus R2 is 0.0112 divided by V2 by V1. So 440 divided by 11,000 square. So this calculation will give me R01. So in fact, let me use the previous code. So I will comment out everything pertaining to X. So X, Z, Z. So the not required lines I have commented out, and R1 I know the value, that is 8.963, 8.963, and R2 value is 0.0112, and then the secondary voltage is 440 and primary voltage is 11,000, and this will give me R01. So let me run it and see. So R01 is 15.963 ohms. So 15.963 ohms. So in fact, I think if I subtract these two, the 960, 15 minus 8 is 7. So I think this term is 7 exactly. Okay, whatever. So let's continue. So I have calculated R1, I have calculated R2, I have calculated R01. The total reactance causes 4% voltage drop and is divided among HV and LV in the same proportion of resistance. Calculate X1, X2 and X01. Alright, so this is little bit tricky. Total reactance means, total means what? It is both primary and secondary together. So I'll consider X01. So X01 causes 4% voltage drop. So what is the voltage of the primary? 1100. So what is 4% of that? So voltage drop in total reactance. So I can write it as I1 square into X01. So this will be the total voltage drop. I'm sorry, not square, just without square. Current into impedance. This is the voltage drop in the total reactor. This voltage drop is equal to 4%. That means 4 by 100 multiplied by the total primary voltage. That is 11,000. So this is what is asked. So I can calculate X01 from it. This the voltage drop is 4% of the total voltage. Therefore, X01 will be this. So 4 by 100 into 11,000 divided by, now what is I1? I1 we just calculated that full load current 8.182 amperes. So 8.182 amperes. So this will give me x naught 1. So let's do that. 4 into 11,000 divided by 100 again divided by 8.812, 8.182, 53.77. So this is x naught 1. Since it is x naught 1, I'll just uh, insert a j here. All right. So how do we calculate x1 and x2? Divided among, so this is among HV and LV in the same proportion of resistance, calculate x1, x2 and x0 1. So in the same proportion of resistance it is divided. So now you see R1 by R01 will be x1 by x01 because same proportion of resistance I want to do that. So therefore this implies that this condition is not always true, but for this problem it is given. So you can always have a different ratio of reactance compared to resistance, but since in the question they had given, this condition holds. So x01 by R01 into R1. So we have all these values. So So x naught 1 is 53.777 divided by R naught 1 is 15.963 multiplied by R1 which is 8.963, 30.195. So this is x1. So once I got x1, now I can find out x2 dash. So what is x2 dash? It is nothing but x2 by k square, which is nothing but x naught 1 minus x1. So which is 53.777 minus 30.195. So I'm getting 23.582. So once I have this, now I can find what is x2. x2 is k square into 23.582, which is nothing but. So here k value already we had defined earlier. So k into 23.582. So I get 0.9433. This is my x2. So calculate x1, x2 and x01. So I have completely everything. So since I have everything, so let me just draw it as an equivalent circuit or just display it in the form of a circuit. So I have voltage, then resistance, inductance, then I have a transformer here, then I have the secondary side, again resistance and inductance. So here there could be a load. So this is 11,000 volts divided by 440 volts and this 90 kVA. And what are the values? So R1 8.963. This is R1. Then X1 equal to J 30.195. So this is the total R. So here R2 equal to and X2 equal to. 9433. That's it. So we have this. And also you just compare typically the R by X ratio. That means the ratio between the resistance and reactance. It is typically 1 is to 4, 1 is to 5 in a normal power system. Of course, here it is quite high, and here it is okay. So always the reactance will be more because we want to have as low resistance as possible. Let's do more problems in next section. Now we look at this problem, that is example 21, and this is quite interesting where it's a complete circuit solution for a transformer. So let's see how it is. So following data refers to a one-phase transformer. Turns ratio is given, R1 X1, R2 X2 are given. No load current is given, and secondary delivers 180. Secondary load is also given with a power factor. Uh, this is T. Determine the primary and primary applied voltage, power factor, and efficiency. So let's to understand this question, let's draw the circuit, transformer circuit here. So I have resistance, reactance, then I have the first winding, then I have the core, and then I have the second winding and its resistance, reactance, and then I have the terminal voltage. So this is V2. There is a load which is given, and the values are given. This is 20 ohms, this is J 100 ohms. So here it is given, and this is 0.05 ohms, and this is J 0.3 ohms. So the impedances are given. Ratio is 20 is to 1. What about voltages? The secondary delivers 180 amperes at terminal voltage. So this is important, terminal voltage. So E2 is not given to us. E2 is unknown. Similarly, E1 is unknown, and V1 is also unknown. Determine the primary applied voltage power factor, whereas V2 is given to us. So V2 is 400 volts. And the delivers 180 amperes. So I2 is also given, that is 180 amperes at 0.8 power factor lag. So power factor is 0.8 lagging. Determine the primary applied voltage. So I want to find this one. So let's do that. Another information that is given to us is the no load current 1.5 amperes leading the flux by 30 degrees. So we'll consider that. So let's try to solve this problem. So obviously we'll begin by taking a reference. So for the time being, let's take V2 as reference. So why I'm saying for the time being is permanently V2 will not be reference. We will change the reference after some time. So right now we'll take V2 as reference. So V2 is 400 and angle is 0 degrees. So but the fact that I'm introducing 0 degrees for V2 means V2 is the reference. So therefore what is I2? So I2 is 180 amperes at 0.8 power factor lagging. So I don't need to use a calculator. Uh, all electrical engineers should know that cos inverse 0.8 is 36.87. So this is nothing but 180 angle minus 36.87 degrees amperes. So this is I2. So now I have the vector representation of both V2 and I2. So y minus, it's because it is lagging. Now if I want to draw the vector diagram, so the diagram is like this. This is V2. So this is 400, angle is 0 degrees, and the I2 is 180, angle is minus 36, or here I can just write 36.87 degrees. So to this V2, I will have to add the drop. So what is the drop in the voltage here? So this drop. So this will be nothing but I2 into Z2. So what is Z2? R2 plus JX2. So which is nothing but 0.05 plus J 0.3. So this multiplied by I2 will give me drop in the secondary. V drop 2. So let's do that. I2 Z2. Let's use my calculator. So I'll just write it as a small code. So I have V2 equal to 400, and I2 I'll define. So capital I2 I'll write it. So I want to define it as a polar number. So the magnitude is 180 given in the question, and the angle is minus 36.87. So this has to be converted to radians. So I have to multiply like this. So this is how I can define I2. So if I now run this code, so I can see on the screen, okay, this is a example 21. So I2 is 144 minus J 108. All right. So I2 I have defined. Then Z2 equal to 0.05 plus 0.3 I. So then V drop 2, that is voltage drop in the secondary, is I2 into Z2. So to be able to draw it as a vector, I want to know the absolute value of V drop 2, and I also want to know the angle of V drop 2. So into 180 divided by pi, just to convert back into degrees. So let me now run this. So here voltage drop is 39.6. So this 39.6 is the drop in the resistance, and this is the drop in the reactance. No, I think that is not the case. But anyway, so this is the final voltage drop, 54.75. So 54.75 at an angle of 43.6 degrees, 67 degrees. So let me mark that here. So this length is, so this is I2 Z2. And this length is 54.75, and this angle is 43.67. Now you can ask a doubt, why am I drawing this at the tip of the V2? So actually it should be drawn at the origin point. This is the voltage drop. This is I2 Z2. But then I want to add this vector to the V2. So for the addition purpose, I am starting this here. So therefore this plus this will be the voltage. So I remove this. So I am drawing it here. So what is this then? This total from here to here will be nothing but E2. So it will be obviously greater than 400. So let's see. So to calculate E2, so I can just write capital E2 is equal to V2 plus V drop 2. So once I have that, again I want to know the absolute value and angle of that. So here I know the magnitude of E2 and angle of E2. Now let's run it. So I'm getting 441.2 and angle is 4.914 degrees. So this is 441.2 and the angle is 4.9 degrees. So E2 is solved 441.2. So let me mark it here. So after solving 441.2 I'm getting. Now I want to find E1. So what is E1? E1 will be like I have the 20 is to 1 ratio. So corresponding to 1 is 441.2. So corresponding to 20 it will be 20 times. So I can directly find the E1. So E1 is equal to, I'll only take, I don't care about the angle right now. I'll explain why. I'll just take E2 and then I'll multiply 20. 20 times the absolute value of E2. So now when I do that, I'm getting 8824.4. I'll just ignore this 0.4. 8824, I'll be taking it. So E1 is 20 into E2. So magnitude of E2. So again 8824 volts. Now let us use E1 as the reference. So therefore, this is my E1. 8824 volts. So the angle is 0 degrees for the E1. So E1 equal to 8824 angle 0 degrees. So why am I doing this is just only to simplify our life. I can actually strictly speaking what is going to be the angle of E1. So if I go here, so E1 will be exactly opposite to E2. So I have to get something like this and this angle will be between this angle will be 4.9. So up to here is 180. So total angle will be 184.9 degrees and all. So I don't want to complicate it that way. I just want to simplify my solution. So therefore I'm changing the reference. So now I can add other things now. So the question is what is I1? And we know I1 is nothing but I0 plus I2 dash. So let's begin by calculating what is I2 dash. So here is where we should be careful. So what is the angle between I2 and E2? So the angle between I2 and E2 is 36.87 is here and this angle is 4.9. So the total angle between I2 and E2 will be 36.87 plus 4.9. So here I am writing angle between E2 and I2 is 36.87 plus 4.9. So that is 36.87 plus 4.9, 41.77 degrees. So this is angle of E2. Now obviously this I2 I1, see this I2 dash will be lagging the E1 and this angle will be 44.77. So angle between E2 and I2 will be equal to angle between E1 and I2 dash. So this is the relation we will be maintaining. And I2 is lagging E2, therefore I2 dash will be lagging E1 and the angle will be 44.71 degrees. Why it is like this? So again, we had painstakingly drawn the vector diagrams in the previous lecture. So you see here, to take any particular example. So let's take this one. So in fact, this is exactly what we are doing here. So you see this angle. This is the angle between E2 and I2. The exactly opposite to E2 we have E1. So this one. This is E1 exactly opposite to E2. Similarly, this is I2 dash exactly opposite to I2. So therefore, this angle will be equal to this angle. So that is what we are trying to do. In fact, this figure is what we can actually refer to when we are working in this problem. So like this. So now I have taken E1 as reference. So basically, you have to completely rotate this reverse way to understand it. So for us now E1 is becoming horizontal. So this whole thing will rotate. Let's go to where we are working. Okay. So now what is the magnitude of I2? So the magnitude of I2 dash. So I2 dash magnitude will be equal to I2 magnitude divided by 20. Why it should be divided by 20? Because the voltage is stepping up, the current will step down. So the current will be 20 times lesser. So what is actually I2 here? So I2 is given the question 180. So I'll divide 180 by 20. So this is 9 amperes. So therefore I2 I know is 9 amperes. So finally if I write it, I2 dash is equal to 9 at an angle of minus 44.71 degrees. So let me define this here. So E1 is defined like this. Now I2 dash, I2D equal to 9 amperes at an angle of minus 44.71 into pi divided by 180. So this is how we can define. So like this. So after changing the reference, now I2 dash I got like this. Now let's come to I naught. So what is I naught? I naught is a no load current. So it's given in the question. No load current is 1.5 amperes leading the flux by 30 degrees. So leading the flux means the E2 will be lagging the flux by 90 degrees. So leading the flux by 30 degrees. So if I quickly, once again, see this is E1, this is the flux, leading the flux by 30 degrees. This is I naught. That means this angle will be 60 degrees. So therefore, I naught is 1.5 amperes, the angle will be minus 60 degrees. Because it is leading the flux by 30 degrees means lagging E1 by 60 degrees. So these two are the currents. Now if I add these two currents, I'll get I1 current. Alright, so let's do that addition. So let me define I naught here. That is 1.5 amperes and into exponent of I multiplied by minus 60 degrees. So into pi divided by 180 to convert into radians. So now I'm getting I2 and I naught both. So now I1 is addition of these two. I2D plus I naught. So this is I1 7.146, 7.63. Now again I'll just display the absolute value and angle of I1. So here 10.454 and angle is minus 46. So let me put that here. So this is 1.5, this is 60 degrees, this is I naught, and then the addition of these two, I am getting I1 somewhere like this. And what is the magnitude? It is 10.4, so it is slightly bigger than this one. So this is I1. So let me just get rid of this. I1 is 10.4 454. Now this I1 will have a I1 R1 drop and I1 X1 drop. So the two I'll add, then I'll get I1 Z1. Then I'll get the V1. So that is the our plan next. So let's, and this angle we calculated, that is 40, 46.8 degrees. So this angle. Alright, so now let's define Z1. Z1 is impedance of the primary. So what is that? So let's refer to our question. 20 J100. So this is there. So 20 plus 100I. So in fact now I have calculated this. So let me also update my diagram. 8824. This is 8824, and similarly I1 I calculated, that is 10.54 something. This is I1. So I1 also adds I2 dash plus I0. Now these two I'll have a drop here. So the drop is nothing but I1 multiplied by Z1. Let's call that as V drop 1, voltage drop in the primary. And let's display the angle, absolute value and angle of that. So let's run this. So 1066 and angle is 31.8. So here you can see, so this is I1 Z1. The value is 1066 and this angle is 31.8 degrees. So now the addition of these two will be my V. So let's just join this. So this is V1. So addition of E1 and V drop. So let's do that. So here V1 equal to, what is that? E1 plus V drop 1. So I'll also display the absolute value and angle of that. So V1 and V1. So let's run this. So 9746 and 3.3 degrees. So this is 3.3 degrees and 9746 volts. So this is how you solve the problem. Now I can attach this vector diagram to this vector diagram, and I can choose V1 as reference or V2 or whatever. I can attach these two vector diagrams and make a one combined full vector diagram. But that exercise I'm not doing. So our objective was to find V1 and we succeeded. So V1 is 9746 at an angle of 3.3 degrees. So I think still some part is left in the question. Let's look at it. So determine the primary applied voltage. We have done that. Determine the power factor. Now what is the power factor? So power factor is nothing but the angle between V1 and I1. So what is our I1? So I1 also we calculated 10.454. Angle is minus 46.873. So if you notice, so this is 46.873 here I'm mentioning. So this angle plus this angle. So this is the total angle between, this is phi 1. So that will be just the addition of these two. So although the minus indicates it is going downwards and this is upwards, so these two we have to add. So phi 1 is nothing but 3.3 plus 46.873. So let's do that. 3.3 plus 46.878. So 50.178 degrees. 50.178 degrees. Now once I have this, I can find the power factor. So power factor is nothing but cos of 50.178, but then cos function requires the angle to be in radians. So I divide by 180 and multiply by pi to convert into radians. So I'm getting 0.64, 0.64 lagging. So this is the power factor of the transformer. So what is the power factor of the load? The power factor of the load is zero point 0.8. Power factor 2 is 0.8 lag. This is for the load. So why the power factor is becoming poor? Because the transformer itself requires reactive power. So therefore some power factor has become poor. All right. What else? I think efficiency is also asked here. So we calculated the power factor. So let's calculate the efficiency. So what is the output? See, V2 I2 cos phi 2 is the output. The total output of the system. So if this is your transformer, this is the transformer box. I don't care what is inside. I'm getting V2, I'm getting I2, and this is the load. And I also know phi 2. So I can find out the P2, that is output power. Similarly, V1, I1 and phi 1 I know. From these three, I can find out P1. So P1 is input, P2 is output. I can calculate the efficiency. So let's do P2. V2, I2 cos of phi 2. So V2 given in the question is 400, I2 given in the question is 180. This is multiplication. And the cos is also given 0.8. So I hope these numbers are correct. 400, 180, 0.8. Okay. So let's do that. So P2 is 400 into 180 into 0.8. So I'm getting 57600 or 57.6 kilowatts. So this is my output power. So what is input? Input is P1, that is V1 I1 cos of phi 1. So that is nothing but 9946. I1 is 10.45 and cos of phi 1 is 0.64. So this quantity will be bigger than this quantity. So let's see. 9946 9946 multiplied by 10.45 multiplied by 0.64. So I'm getting 66519. So 66510. So be careful with the units. So sorry, this is 0.0. So therefore this is 66.519 kilowatt. So now I have these two. So I run out of space. So let me calculate the efficiency here. Efficiency is P2 by P1, output by input. That is, so if I store this as P1, so EFF equal to P2 divided by P1. So 86.59%. So this might seem little low, but actually for a practical transformer, the efficiency as high as 95, 96, or even 98%. So the transformers are highly efficient. So I hope you learned something from this problem. So let's do more. All right, let's do one more quick problem to end this video. So just here is a question. You can have a look at it and you can attempt it. This is a short one, so let's get starting. So what's given in the question? Calculate the effective resistance and leakage reactance refer to the primary of the transformer. That means calculate effective resistance. That means R01 is what and X01 is what. So these questions are asked. Calculate the effective resistance and leakage reactance referred to primary. So that's what is. which gave the following data on test with secondary terminals short circuited. Okay, so let's see what is going on here. The secondary terminals are short circuited, so completely short circuited. That means I know V2 equal to 0, and of course not E2 is 0, there will be some voltage drop. Applied voltage is 60 volts. Alright, so here you are applying V1 equal to 60. Current is 100 amperes of current, and the input power P1 is 1.2 kilowatts. So of course what is P2? P2 will be 0 because V2 is 0. So 1.2 kilowatts is the input power. Now one thing you should realize is that when the secondary is short circuited, V2 is 0, E2 will be very low, E1 also will be low than the rated one. So therefore, the applied voltage actually 60 volts is also actually low. This is not a rated voltage. The rated voltage may be as high as 2000 volts or more. So a partial voltage is applied. Under that condition, the flux in the core is not complete. So therefore, I can ignore the iron losses. So that is the first thing you should know. Secondary short circuit means V2 equal to 0. Therefore, uh, V1 V1 applied will be fraction of rated V1. So therefore, ignore core losses. Core losses are iron losses. So therefore, whatever loss occurs, that 1.2 kilowatt is nothing but, therefore, all the losses are copper losses only. So the copper losses happen in the secondary winding and the primary winding. Both will get heated up. But then I think we don't require that individually, because the question is asked what is R01 and X01. So let's find out first impedance. So how do you find out impedance? So Z01 is nothing but V01 by I0, I1 short circuit, whatever. So or V1. So whatever, we are applying 60 and the current is 100. So this is 0.6 ohms. So because 60 volts and 100 amperes, so that means the impedance is 0.6 ohms. But then how much is the R and how much is the X, we don't know. But then I can know the power factor. So how to know the power factor? So P1 is V1 I1 cos of phi1. So 1.2 kilowatt, so 1200 watts is equal to V1. V1 is 60, I1 is 100, and therefore cos of phi1 is what is left. So from this, cos of phi1 will be 1200 divided by 60 into 100. So zeros go. So 12 by 60, or 6 2s are 12 and 6 10s are 60. So 1 by 5 or 0.2 is the power factor. So once I know the power factor, then R by Z is also the power factor. Therefore, R01 is nothing but 0.2 into 0.6. So 0.12 ohms. Then X01 I can calculate Z01 square minus R1 square. So that is 0.6 square minus 0.12 square. So that is square root of 0.6 square minus 0.12 square. So 0.58788, or I'll just round it to 0.588. So I'll introduce J and then call it ohms. So therefore, R naught 1 plus j x naught 1 is equal to 0.12 plus j 0.588. So this is the final answer. I hope you also got the same answer, and I hope you learned something from this problem. Thus, in this video, we had solved a few problems related to transformer with impedances given. Let's learn something more like constructing equivalent circuit of a transformer and all in the next lecture. Thank you.